welcome back to another week's content. This is Design the Engineering Process, a channel where we give a walkthrough on process engineering operations and design. In today's content, we will be looking at two very important equipments used in process engineering operations and design: the pump and the valve. To be more specific, the control valve. Let's dive in. Let's start with the pump. What exactly is a pump? A pump is a mechanical device used to move fluids, gases, and liquids from one place by adding energy to the fluid majorly through pressure. Types of pumps include centrifugal pumps, peristaltic pumps, positive displacement pumps. Under the positive displacement pumps, we have reciprocating pumps, rotary pumps. As their names imply, the reciprocating uses pistons to change pressure, thereby moving fluids. Rotary pumps use rotating elements to change the pressure, thereby moving fluids. Now, a pump is slightly different in ASPEN HYSYS due to its efficiency. From a normal pump in a real-life scenario, a real-life operation is a device used to increase energy majorly through pressure in both gases and liquids. But for ASPEN HYSYS, there is an exception to that. A device used to increase the pressure of liquids, specifically liquids. ASPEN HYSYS makes use of the centrifugal pump as it is more efficient for liquid pressure increase. So take note that centrifugal pumps don't pump gas due to the compressible nature of gas. What this means is that pumps utilize the incompressible factor of a fluid to actually increase the pressure and move the fluid from one point to another. For gases, they do have a compressible nature. When force is exerted on them, they compress themselves. But fluids, liquids, to be precise, they are incompressible, so you cannot compress them to actually stay in a specific contained state. We're back to the modeling environment to see what a pump looks like in action inside ASPEN HYSYS. So, remember, the first thing to always do before you start simulating and modeling in ASPEN HYSYS, you select your component list and fluid package. If you do not know how to do that, the link will be dropped in the description. As always, please make sure to watch your previous content to avoid getting lost. So, for today's content, we will be using our component. We will be having our component to be H2O, water, and our fluid package, as always, the very versatile Penn Robinson. So we start, as always, by dropping a stream, and since we're using water only for components, we can just call this H2O. H2O. Let's go on ahead and give a composition. It's only water we're having, so 100% water. And we need to specify some other parameters. Let's say it's at a temperature of 25 Celsius and 10 bar. Having a flow rate of 1000 kilomole per hour. Perfect. So remember what we said about pumps in ASPEN HYSYS. They only increase pressure of liquids, specifically liquids, no gases, because we make use of a centrifugal pump in ASPEN HYSYS. Now, what if we do have a mixture of gas and liquid? That's a no-no for the centrifugal pump in ASPEN HYSYS, because gases inside centrifugal pumps cause a phenomenon known as cavity, basically having holes in your pumps, and that is not desired in a process operation. That damages your equipment. So centrifugal pumps are supposed to be only increase pressure for a fluid of liquid, 100% liquid. So our vapor fraction for a pump operation will always be 0, 100% liquid. So our pump is our fourth equipment, rather sixth equipment in our model palette. And as always, like every other equipment, it looks red when empty. But then when we double click, we can see the design environment where we plug in our inlets and outlets. So we have our inlet on ground, which is H2O, and we can just call the outlet pumped H2O. And like some other equipment, our pumps do require energy labor. So you can just call this E-pump. That's perfect. And we have a message down here in yellow, unknown duty, basically telling us we have to specify more. I have to give more details. Since a pump is used for increasing pressure, but as a result, it changes our pressure, our temperature rather. For gases, we do know that increase in temperature leads to increase in pressure, but for liquids, it's a little bit not too direct. Sometimes we do have a direct proportionality. Sometimes we do have an indirect proportionality. But remember, in our pump, centrifugal pump, we are dealing only with liquids, so we don't expect that an increase in pressure will always lead to an increase in temperature. But let's try that out and see. A pump is supposed to increase our pressure, so we can specify our pressure inside our worksheet. Let's say we are pumping this H2O from a initial pressure of 10 bar to 20 bar. Let's give it 20 bar. Perfect. And ASPEN HYSYS automatically finds the temperature and pressure for us because this is an equipment solely for increasing pressure. So we specified our pressure, and ASPEN HYSYS iterated to give us the other two parameters, the temperature and the vapor fraction. Remember, ASPEN HYSYS does not simulate fluid flow. So our flow rate, our fluid flow wouldn't change that much. It's more of a constant factor. But in a pump, when dealing with liquids, we are majorly after the increase in pressure. And that's what we just attained. An increase in pressure from 10 bar to 20 bar. And as you can see, our temperature slightly went up from 25 Celsius to 25.09 Celsius. Now, if this was a gas, even though pumps cannot actually increase the pressure of gases, but if this was a gas, it's already a written factor, a stated factor that increase in temperature leads to an increase in pressure. So after correctly connecting our pump, it changes its color from a red color to a silver color. And with this, we have successfully operated our pump. But let's just go back and confirm what we've been saying. Let's tweak this temperature to about 180 to make our vapor fraction gas. That doesn't work. Let's say 200 Celsius. Yeah, that's perfect. So it's currently a gas, the inlet. And you can see the pump is having a very funny outline of a yellow color on it. But let's go in and see. And we have a message down here in yellow saying vapor and inlet stream. Basically telling us that there is gas inside our pump. And with that, ASPEN HYSYS cannot successfully operate the pump. So it has to be always liquid, 100% liquid, not 0 point anything. It has to be plainly 0.0, 100% liquid to operate a pump successfully. With that, we have successfully operated a pump. Our second equipment for the day, a control valve. What exactly is a control valve? A mechanical device used to regulate fluid flow, pressure, and as a result, temperature. Remember that there is a relation between pressure and temperature. For liquids, it's always directly proportional, sometimes directly, sometimes indirectly, but for gases, it is always directly proportional, temperature and pressure, like we have always been saying. So, types of control valve: globe valve, ball valve, butterfly valve, gate valve, pressure reducing valve. So, as for ASPEN HYSYS, what is a control valve? It's a device used to decrease the pressure of both liquids and gases in operations. Unlike our pump, which 100% deals with liquid, our control valve differs. It deals with both liquids and gases. So, as a result, temperature changes due to the relationship between As a result, temperature changes due to the relationship between temperature and pressure. Yeah, like we said earlier, the relationship sometimes directly, sometimes indirectly. But since ASPEN HYSYS doesn't simulate fluid flow, this is constant. That's the fluid flow. The fluid flow doesn't change in real life operation. We expect that if we have a valve which controls the fluid flow, if it's closed, then we expect our fluid flow changes from in the initial fluid flow would differ from the final fluid flow. But in ASPEN HYSYS, it's not always like that because ASPEN HYSYS doesn't 100% simulate the fluid flow. It's hard to tell. So it majorly deals with the temperature and pressure parameters, even in our control valves, just like our pump. So let's look deeper into the valve operation. What we have here is a valve scenario one, a valve open, 100% open. On the left hand side, we have the inlets, the fluid molecules. You could imagine them to be gases or liquids, whichever one you find more convenient. On the left hand side, we have the inlets, the fluid inlets. It goes in, the valve is 100% open, completely open. And on the left hand side, we have the fluid outlet. What goes in is equal to what goes out because the valve is completely opened. Now, for the second scenario, we have a valve completely closed, shut down. So with this, what we have on the left hand side is not equal to what we have on the right hand side. The inlet is actually filled up with fluid molecules, but on the outlet, the side of the outlet, it's empty because the valve is completely closed. It's basically like a gate, like a door. It's closed, and as a result, nothing can pass through. The third scenario, a valve half open. It's not completely closed and it's not completely open, in between, partially opened. So what goes in is still not equal to what comes out, but it's better than the closed scenario. The half open scenario, we have a little bit of our fluid coming out, not just 100%. So the inlet is not equal to the outlet, but nevertheless we do have something coming out in the outlet, just in a lesser amount. Once again, we're back to the modeling environment. This time around, we're going to take a look at the operation of the control valve. The servant equipment on our model palette, but just before we go down to it, we have a relief valve down here. It's also a type of valve, but it's majorly used for pressure relieving equipment, a little bit more complex for the beginner's journey. So hopefully in the future we take a look on its operations, but it's basically a valve that reduces pressure, decreases pressure in a pressure in an equipment or a pressure or a process operation that has a lot of pressure, excessive pressure condition. It relieves, like the name implies, it relieves pressure, excessive pressure in an operation. So our servant equipment, which is the control valve, and we also drop a string. So once again, we in this H2O. So let's give a vapor fraction of 1 gas this time around. A pressure of 10 bar also. Flow rate of 1,000 kilomole per hour. 100% water. If that we've successfully created our stream. And yes, a temperature of 180 Celsius, vapor fraction of 1 gas, pressure of 10 bar, and molar flow rate of 1,000. So we're clicking on our control valve. We connect our inlet to our H2 and the outlet to be let's call it valve out outlet. So we need to specify our change in pressure, and there are two ways to do that. In here, when we click on the worksheet, as always, we have our parameters. You can just come down here and increase and specify your change in pressure. Remember, this is a valve, it decreases pressure, so the pressure is going to be less than 10. Let's just say it's 5. With that, we've successfully operated our valve. As you can see, silver color with the green highlighted green color saying okay, so we've successfully operated our valve. And take note of the pressure. Inlet temperature was 180 Celsius and its outlet temperature is 172.2 Celsius. Remember, direct proportionality of temperature and gas temperature is a function. Direct proportionality of temperature and pressure in gases. Temperature is a function of pressure, directly proportional. So increase in temperature leads to increase in pressure, and the decrease in pressure leads to decrease in temperature. That's what we just witnessed. So this is one way to actually operate your valve, specifying the change in pressure. That's the delta P. Let's just erase this. The second way is to come down here to your design and click on parameters. And you have a function here, delta P, where you specify the change in pressure. So we manually, for the first scenario in the worksheet, we manually calculated it to be 5. We wanted our outlet pressure to be 5. So that means that our change in pressure, remember, just like change in temperature, it's final temperature minus the initial temperature. So it's the same thing for change in pressure to final pressure minus the initial pressure. So we just specified our change in, we specified our outlet pressure, and ASPEN HYSYS automatically did the calculation behind the screen for the change in pressure. And if we do that manually, we know that that's the change in pressure is a negative 5 bar, a lost pressure. So, but here we do specify the amount we want for the change in pressure. Let's say we want a 3 bar change in pressure of 3 bar. We enter 3 bar and it automatically calculates our outlet pressure for us. Yes, our outlet pressure to be 7 bar. 10 minus 3 gives us 7 bar. The change in pressure that will be specified over here, 3 bar. It deducts 3 bar from our initial 10 bar, giving us a 7 bar. So let's say this is 8 bar. Our change in pressure is 8 bar this time around. We expect our outlet pressure for our H2O to be 2 bar, which it is. As you can see, the temperature further reduces to 167.5 Celsius. So, like we said, the valve is supposed to control the fluid flow, but ASPEN HYSYS doesn't simulate fluid flow, so it just has to remain constant. Even if we do decrease our pressure, the fluid flow can't actually change because ASPEN HYSYS doesn't simulate fluid flow, so it just has to remain constant. But our pressure and temperature change, and in some instances our vapor fraction also changes. So that is the operation of a control valve in ASPEN HYSYS. A very small and simple equipment that does wonders in process engineering. So let's try another scenario where we have our vapor fraction to be liquid, 100% liquid. Yes, we have liquids. When we go over here, you can see it's still okay. Our valve is still successfully solved. Everything is fine because the valve operates both gas and liquid. It doesn't matter, unlike the pump, which deals 100% liquid. But remember, we have a change. There's a little bit of a change over here. We have our vapor fraction. The outlet vapor fraction differs from the inlet vapor fraction. During the process of decreasing the pressure and temperature, gases were formed. A bit of gas. We do have gas as our outlet this time around, and it's a little bit more of a complicated phenomena for this gas. It's something that we need to talk in depth about. Hopefully we will do that in the future. But with this, we have successfully solved our valve in a liquid operation, a liquid operation using a control valve, and a gas operation using a control valve. And with this, we have seen that you can actually control the fluid flow, the pressure, decrease the pressure of both liquids and gases using a valve in ASPEN HYSYS. And luckily, today's content is a very simple and short one. And with this, we come to the end of today's content. If you follow us as always down this far, please make sure to subscribe, like, and click on the notification icon, as this will go a very long way to motivate us to create more content like this. Thank you very much.